and talk about additive convolutions, joint work with Jonathan. And then we're going to have the reception after this.
Yeah, thanks. Thanks so much for the organizers for having me. Yeah, so this is part 2 of Jonathan and I's obsession with the finite convolutions, but from a different point of view, and this time with more theorems. So I'm going to kind of go over some things that probably are pretty basic, but I'll try to move through them quickly. So the point of view that I'm looking at this from is one that we're all very familiar with, real-rooted polynomials used to encode information about combinatorial objects I'm interested in, either in terms of the roots or the coefficients. And the main power of this interface is that operations on the combinatorial objects I care about correspond to linear operations on these polynomials. And so under this interface, then, I'm really interested in questions about linear operators. And so there's some classic ones which have been referenced here, which are the Pullier-Schur theory questions. Which linear operators preserve the set of all real-rooted polynomials? And also, which linear operators preserve the set of real-rooted polynomials of bounded degree? These are two separate questions, and they're classic questions. And what I'm going to look at today is an abstraction of these questions. So I'm going to call a polynomial one mesh if it's real-rooted and the minimal distance between any pair of roots is 1. So this gives some condition on the spacing of the roots. And so we have these two discrete Pullier-Schur questions. Which linear operators preserve the set of one mesh rooted polynomials? And which linear operators preserve the set of one mesh rooted polynomials of degree at most n? So I'm going to talk a little bit of the background of this theory and talk about our contributions. So let's start with some really basic stuff in the world of real-rooted polynomials and see how that abstracts and relates to things in the finite difference realm. So we're very familiar with the fact that derivative preserves real rootedness, and an instructive way to see this is to study the graph of p prime over p. It's a graph you've probably seen before. And by studying the graph of p prime over p, we notice that the zeros of this graph are exactly the zeros of the numerator, which encapsulate the fact that p prime is real rooted. And if I move the x-axis, which corresponds to shifting this function up or down, then I will get exactly n real roots, no matter which way I move it, which corresponds to the fact that p prime minus alpha p is real rooted for any alpha. So we get this nice result, a very standard result. And we can compose these then. So if the operator I minus alpha id is real rooted for any alpha I, then if I compose these operators, I get real rootedness. And so I like to think of this guy right here as a polynomial in D. And it's a polynomial in D where if I wrote it as p of D, then p would have real roots. And so we could ask more generally which polynomials in D, which I'll call differential operators, preserve real rootedness of unbounded degree. And it's a theorem, an older theorem, that the differential operators which preserve all real-rooted polynomials are exactly the ones which come from real-rooted P. So how does this relate to the mesh case? So first, let's do some definitions. So like I said earlier, I'm going to call the minimal distance between two roots of a polynomial its mesh. And we say a polynomial is b-mesh if it's real-rooted with mesh at least b. So any real-rooted polynomial is going to be zero mesh because the minimal distance will be at least 0. And there's a nice characterization of b-mesh in terms of interlacing that I'll be using a lot throughout this talk. So here I've picked some arbitrary polynomial p with these brown dots, and I've shifted it to the right by b with these blue dots. And what does it mean for it to be b-mesh? An equivalent thing to say is that this shift interlaces my original polynomial, which is nice. There's also an equivalent definition, which is like kind of the multiplicative definition. So if I have a positive rooted polynomial, I could look at the minimal ratio between roots, where maybe I'll pick the convention where I'm always looking at the ratio of the larger root to the smaller root, and I say it's q mesh if that ratio is bounded below by q. You could also do it the inverse way. OK, so what can we leverage from this interlacing fact? So p of x and p of x minus b interlace. And so I can look at my picture again, and I get a very similar picture by interlacing. So here the blue dots are the roots of p, the numerator, and the brown dots are the roots of the shift of p. And now what happens when I shift the graph? Well, the key observation is that these black intervals here are exactly b units long, because all it is a shift of b. And so if I shift my x-axis up, what happens? I get roots which lie between this unmarked interval right here. And if I think of the distance between these roots, within each of these intervals, between these green roots, I have a black interval. And this black interval, like I said, is exactly distance b. So this proves that these green roots have to be at least b apart. But notice if I would have gone the other way, I would not have gotten such a result, because I could have had my roots coming in much quicker on one of the intervals here than on the other. So the spacing could become less than b. And so we see when we look at what it means to shift up, I get this polynomial, identity minus alpha shift. And now I've seen identity minus alpha shift. It will also be b mesh if alpha is positive. So we can play the same game. So I'm going to call S the shift operator, here shifting to the right. And I can compose them. So now I get a polynomial in shift operators. And I see that this polynomial is going to preserve b mesh when the roots of this polynomial are positive or non-negative. Ask the same question, which shift operators preserve b mesh? And this is a theorem of Brondin, Krasikov, and Shapiro from 2016, that a shift operator preserves a set of all this should say a shift operator preserves a set of all b mesh polynomials if and only if this polynomial is real rooted with non-negative roots. So we get it. So we've shown one direction here, the kind of simple direction. The converse is the direction that they prove. Okay. So what have we done? Remember the Polya-Schur question. The first one is, which linear operators preserve b mesh polynomials of all degree? And we've answered the question for a very specific type, a very specific family of operators, namely operators that are polynomial in the shift operator. There's another type of classic family of linear operators that were studied, and that's diagonal operators. And diagonal operators are just those for which x to the k is an eigenvector. And there's a classical theorem of Polya-Schur, which says that a diagonal linear operator preserves the space of all real rooted polynomials if and only if t of e to the x is a limit of either positive or negative rooted polynomials. And what does t of e to the x mean? Well, think of e to the x as a power series, and since t is diagonal, we're just applying to each monomial in that power series. And so there's an equivalent result here that was proved by Lamprecht in 2016. So we have to unpack this. So this one is no longer about b mesh like the shift operator one was. This one's about log mesh, so the ratios of the roots. And it says that a diagonal operator preserves the set of q log mesh polynomials if and only if t of the q exponential function is the limit of either positive or negative rooted q log mesh polynomials. And here the q exponential function is this guy. And notice that if I let q limit to 1, what happens? Well, maybe not obvious, but if I let q limit to 1 under appropriate normalization here, I'll get the exponential function. I need to normalize things. And down here, the set of 1 log mesh polynomials is just all positive rooted polynomials. So I recover Polya-Schur. So that answers the first question of Polya-Schur in the discrete setting for two families of operators, shift operators and diagonal operators. And you can ask, what about the general case? So there's the Brondin result of 2008, which classifies linear transformations which preserve real rootedness. You could ask, can we get something like this in this case? And I'm curious. I do not know the answer to that. So you need a multivariate notion of b mesh or q log mesh or the combination of the two. I have some ideas about this, but currently this is still open. OK, so that talks about the unbounded linear operator case. What about the bounded linear operator case? So why would we study the bounded linear operator case? Well, the set of linear transformations which preserves bounded degree is going to be larger than the set of transformations which preserves all unbounded degree. And often in applications, when I've encoded my combinatorial object, I'm interested in studying polynomials of bounded degree. So this gives us more flexibility. And so this is just a very small example of a differential operator. It preserves all real-rooted quadratic polynomials, but it does not preserve all real-rooted polynomials. And in fact, P is not real-rooted. OK, so enter the additive convolutions for the third time. I won't belabor this because we've seen this before. Although, maybe I think we've seen both these definitions. So you can write the additive convolution as a differential operator. And Jonathan was great to point out a lot of properties of this. We can think of this as representing any arbitrary differential operator. And it has nice properties like commutation with shift, with scalars, with derivatives. It's commutative, associative, so on and so on. And we have the multiplicative convolution, defined kind of on a basis. So it's kind of more of a diagonal action. And it also has many of those same properties. And I just want to quickly point out the two other definitions that we've seen. There's a random matrix interpretation, which shows up a lot in applications. And there's the root definition, which Jonathan also mentioned, which I will use later. OK. So a theorem that was mentioned earlier is that a real differential operator preserves polynomials of bounded degree at most n if and only if it can be written as additive convolution by a fixed polynomial. So let's go back to that example I had. Here, my example was d squared plus 2d plus 2i. This comes from a polynomial which is not real-rooted, but can be written as convolution by a real-rooted polynomial. So this tells us right here, since x plus 1 squared is real-rooted, additively convolving with it will preserve the space of quadratic real-rooted polynomials. But because it doesn't come from a real-rooted polynomial itself as a differential operator, it's not going to preserve all real-rooted polynomials. So this is, in my opinion, the crux of why the additive convolution is so powerful. And we get a similar result for the multiplicative convolution, this time with positive rooted polynomials. And yet again, Brondin in 2008 proved a result which covers all linear operators, which preserve bounded degree real-rootedness. OK, so our path forward is to figure out if we can mimic these results. So I'm going to kind of show you a really basic combination of properties that I'm going to leverage multiple times in this talk. And that is that the additive convolution preserves interlacing. You can see this for the classical additive convolution from the fact that it's bilinear and it's real-rooted preserving. And also that it commutes with shift. And combining these, I'm going to get mesh preservation. So let's see how I can do that. So I start off with a polynomial that's b-mesh. And yet again, that means that p is interlaced by its b shift. I now convolve by any real-rooted polynomial. And I know convolving by a fixed real-rooted polynomial is going to preserve interlacing. So I know p convolve r is going to be interlaced by the p shift convolve r. And now I can commute my shift out of the operation from shift commuting of the additive convolution. And I see p convolve r is actually interlaced by p convolved r shifted. And therefore, p convolve r is itself a b-mesh polynomial. So we see the classical additive convolution preserves mesh. And this backs up the intuition that Jonathan was talking about. We have this intuition that the additive convolution is constantly spreading roots. And this is one way to quantify that. It says if you take any two polynomials and you additively convolve them, the minimal distance between them is the max of the minimal distances of your inputs. So you can never shrink roots in. There are a lot of other ways to quantify this. There's the entropy conjecture that people are really interested in. There's submodularity stuff. But this is just one way to quantify that. And you get the same thing for the classical log mesh preservation. So nothing I've written here is particularly deep. But notice what this says. So what does it say? If I fix a b-mesh polynomial p, then that linear transformation will send any real-rooted polynomial r to a b-mesh polynomial, which is the additive convolution of them. So I end up with linear transformations which send real rooted polynomials to b-mesh polynomials. And that's not what I'm particularly interested in. I'm really interested in the more general question of sending b-mesh polynomials to b-mesh polynomials, not real rooted polynomials to b-mesh polynomials. Okay. So what do? We look at finite differences. So some of these are probably familiar, and maybe some of these are not. So this is just the additive finite difference. If I limit b to 0, I get the classical derivative. This is what's usually called the q derivative, and this I'll call the polar q derivative. And if so these are well-studied objects, and Fisk, in fact, in his giant book of polynomials, has a whole chapter about affine transformations and how they affect polynomials, and he studies a lot of properties about these kind of things. One of the nice things he proves, which is pretty elementary to show, is that the finite difference preserves b-mesh, and both of these q derivatives preserve q log mesh. And so we can think of these as generalizations of what's happening in the classical case. When I limit b to 0, I'll recover the classical derivative here. And when I limit q to 1, I'll recover both the classical derivative here and the polar derivative with respect to 0 here. So maybe dy. And so now I have this kind of picture in my head. I have the classical case, the classical realm, where I have tools like real rootedness and the classical derivative. And I have their corresponding tools in the finite difference case, like b-mesh and the finite difference. So what do? I define the kind of obvious abstraction in the additive case at least. So for the additive case, I just replace my derivatives with my finite differences. In the multiplicative case, I have to replace things with something maybe not as natural, but these are q binomial coefficients scaled in an appropriate way. And so a theorem of Lamprecht from 2016 is that if p and r both have q log mesh, then the q multiplicative convolution has q log mesh. And it should be noted that this is like tight in a way. So if I, for example, take a q log mesh polynomial p and a real or positive rooted polynomial r, I won't even get a positive rooted polynomial out. I'll just get something maybe with complex roots. So the q log mesh really is a boundary condition for this convolution. And so Jonathan Nye's theorem is the same thing, but for the additive convolution. And this was originally conjectured by Brondin and Shapiro and Krasikov in 2016. This additive version. In the same paper, they proved the unbounded version. Okay, so this is what we're going to set out to prove now. Any questions about the setup? Okay. Oh yeah, it should be mentioned that this all kind of Lamprecht's proof and Lamprecht's results are all inspired by papers from the 70s of suffrage, where he looked at similar results for circle-rooted polynomials. But he ran across this from a completely different field in a completely different way, studying star-like domains and the such. So it's a pretty interesting crossover. OK. So Jonathan and I proved this theorem in two separate ways. We kind of proved them simultaneously in these two ways. One way we do it is by taking Lamprecht's proof, distilling it down to what it needs, and making the appropriate modifications for the additive case. So his proof doesn't just copy over to the additive case, which is, I presume, why he didn't do it. But once you make the appropriate modifications and you realize what you need to substitute in, you can get it. Simultaneously, we didn't really think that this would work, so we asked a more general question, which is how can you take results about multiplicative convolutions and transfer them over to additive convolutions, just in a very generic way. And we developed a framework to do this. So I'm going to talk about both of those methods here. So like I said, the main thing we like to do, interlacing preservation plus shift commuting, is going to give us mesh results. And this was Lamprecht's main idea. He proved this for the q multiplicative convolution. If you take a q log mesh polynomial p, and r and s here are just positive rooted, not q log mesh, then oh, I lied earlier. OK, if you have p q log mesh, it does preserve real rootedness. Then p being q log mesh, so if r and s interlace, then p being q log mesh implies that this convolution by p will also preserve interlacing. And just like we saw earlier from the fact that we get commuting through the additive convolution, once we get interlacing preservation, which is the main theorem of Lamprecht, we're in fact going to get mesh results. So we're going to get this result down here, that the log mesh of the output of two Q log mesh polynomials is going to be Q log mesh. So the Q multiplicative convolution preserves log mesh. And this is our theorem. We prove when we're mimicking Lamprecht's result, we do the same thing for the additive. So the main thing to take from this slide, I know it's a lot of words, is that interlacing preservation is key. You might try to set out to just prove the fact that mesh is preserved under these additive convolutions, and that's pretty tricky, and it's not clear how to proceed. Really what you should do is prove the stronger result, that you get interlacing preservation, and that will, with shift commuting, imply mesh results. And I think there's some really interesting things that he does that we hadn't run across before that I want to just kind of point out here. So in general, when people talk about linear operators that preserve interlacing, often they'll say something like a linear operator which preserves all real-rooted polynomials preserves interlacing. But we don't have that here, and so we need another criterion. And our criterion, or Lamprecht's criterion, I should say, is based on this really nice observation. So if you fix a polynomial f and you look at all polynomials which are interlaced by f, it's a cone in the space of polynomials, and that cone is finally generated. And it has really nice generators. It's generated by f, negative f, and all polynomials you obtain by taking f and removing one of the roots. So it's pretty easy to convince yourself that all of these things are interlaced by f. And then it's maybe less easy to convince yourself, but not so difficult to do, that all things that are interlaced by f are in this cone. And you can do this using partial fraction decomposition. And so now what do we want to do? If we want to show a linear operator t preserves interlacing with respect to a specific polynomial f, we just need to check it on these generators. And this is Lamprecht's proof. He takes the generators, he inducts on degree, and he uses the nice properties, commuting relations, and Q-log preservation of his two nice derivatives. But his proof really needs a polar derivative. And it turns out in the additive case, you don't get a polar derivative. So this is the natural polar derivative. Don't worry too much about the symbols, but just worry about this punchline. It doesn't preserve b-mesh. So if you try to construct what would be the natural polar derivative, the dy alternative in the finite difference case, it doesn't exist. And so his proof falls apart. And so instead, we kind of come up with an approximation to it. So we have this nice technical lemma which says if you fix a specific polynomial f, then you can take a pole that's really close to 0. And for poles close enough to 0, your polar derivative will preserve b-mesh, and it'll have the interlacing properties you want. So you don't get a universal polar derivative that works for all f. But for fixed f, you can find an appropriate polar derivative. And this is fine, because at the end of the day, the kind of results we want to prove are that b-mesh convolution with respect to a fixed polynomial preserves interlacing. So we've already fixed the polynomial in our argument, and so we can get away with this kind of substitution. OK. So that's Lamprecht's proof. I think it's nice because it contains a lot of nice ideas. But for the most part, they're Lamprecht's ideas. So what about our contribution? So how to transfer results from the multiplicative setting to the additive setting. So in general, there's all kinds of results that people care about for these convolutions. And if you look at any of the papers that prove them, they prove them separately for multiplicative and additive every time. And sometimes it can be very tedious to do that. So even like off this list is the MSS results, which they also prove separately for multiplicative and additive. And so we came up with the question, it seems like every time you come up with a result for one, you get a result for the other. There must be some connection between the two. OK, so I'm going to go through a bit of a calculation here. Hopefully the colors will make it doable. So let's start off with the multiplicative convolution. I write the multiplicative convolution down in the root form. Yet again, I'm summing over all what I can think of as matchings between the roots of p and r, where this polynomial right here, it's a polynomial degree n, where the roots are just pairwise products of polynomials of roots of p times roots of r. And I'm summing over all possible pairings. I want to somehow make this additive. So what I do is I introduce a new variable. I introduce a new variable q. And I normalize. Don't worry too much about the normalization. So when I do this change of variables, I input my new variable q, and all the dust settles. What happens is I end up down here with something x, some constant, and now the linear part with respect to 1 minus q looks like the additive convolution, and then some error. So if I now post-compose to make this part look nicer, what do I end up with? I end up with the additive convolution plus some error term that goes to 0 as q goes to 1. So this shows this theorem, that by precomposing and postcomposing by the appropriate functions in q and x and limiting q to 1, I can take the multiplicative convolution to the additive convolution. And notice this all makes sense. These are still polynomials in x, so the multiplicative convolution is well defined. I can postcompose here. Everything is good. And in fact, this converges uniformly on compact sets. But this is a kind of a mess. So what's the intuition here? Well, there's actually some really nice intuition, I think. So we would like to think of this as exponentiating and taking log of the roots. And this is kind of what is happening. So if I wanted to exponentiate my roots, what I could think of doing is precomposing by log base q of x. Now this doesn't really make sense, because I take a polynomial and now I end up with a polynomial in log. But at least the real zeros will go like this. This is the transformation of the real zeros. And I could do the same thing over here with a logarithm of roots. And so, I have this intuition that I have this formula for the multiplicative convolution. If I could exponentiate my roots, then I'd end up here. Of course, now I get this. And now after all the dust settles, I'm going to try to take a log of my roots. So first I exponentiate, then I take multiplicative convolution, then I take log. And this is kind of what I'd hope to happen. This is vague, because it's intentionally, it's not actually what's happening, but it's the intuition for what's happening, because if you take log base q of x and you write it as a Laurent series in q and x about 1, the first term that appears is 1 minus x over 1 minus q. So this is the crudest approximation you could take to it. And if you take q to the x and you do the same thing, this is your linear approximation. So in a way, we're taking linear approximations of these. Of course, this is not going to give us a true result for any q, but by limiting, it washes away what's happening. This is the intuition on how to connect the multiplicative to the additive. And I wanted to show you a really silly toy example to show how this could take results from the multiplicative realm and put them into the additive realm. So I'm going to take the result that the multiplicative convolution preserves positive rootedness, and I'm going to make that into a result that the additive convolution preserves real rootedness. Here I put q to the x in here. This is actually what we proved. We didn't use the linear approximation of it. You can use either. But in our paper, we constantly use q to the x. But we do need to use this approximation for log, because it does not make sense to plug in anything here, because the multiplicative convolution is only defined on polynomials. So we really do need the log approximation in my precomposition. So I take two polynomials which are real rooted. And I want to show that this is real rooted. So what happens when I apply this precomposition to them? Well, the roots go to 1 minus q ai. So as q goes to 1, these roots are getting really close to 1. So for q close enough to 1, my roots are positive, which means these two polynomials have positive roots, and this preserves positive rootedness. So when I have, by hypothesis. So when I do the multiplicative convolution, I get positive rootedness. So now what happens when I compose q to the x? Well, I have to be a little bit worried because I have infinitely many roots, but basically the band on which I have roots is growing large as q approaches 1. And this converges uniformly in compact sets, which we show. And so because this has positive roots, the real roots of the thing that this converges to will also have, the roots of the thing that this converges to will also have real roots. And so we can easily get that P additive control of R is real rooted just from this fact. I mean, this is a very silly example. You can prove these things in a million ways. Neither of these results are difficult. But for an example of a difficult result, or somewhat difficult result, would be the one that we want to show. So we have the Q multiplicative convolution preserves Q log mesh. We want to show that that implies the B additive convolution preserves B mesh. And this is where things get really tricky.
Before you go on to the trickiness, can I ask?
Yeah.
What happens if you start with if you replace the multiplicative convolution with just additive, and then do this funky operation? What does it become? Like multiplication becomes sort of addition. What happens to addition? Do you know?
Yeah.
Jonathan, do you have any intuition about
No, I don't know. I don't know what you would get. Yeah.
Okay.
I mean, I guess you would roughly assume like you would start with addition here, exponentiate, log. I mean, you can roughly get some intuition based on that, but I don't have a better answer than that. Yeah.
Could be interesting.
Yeah, definitely something to consider.
I mean, if you had negative roots, something might go wrong, right?
Yeah, you'd probably need to start off with positive roots, or even in that case, you might need to start off with roots greater than 1. But I mean, you can always kind of play these games. Okay, so how do we get to the Q and B convolutions? Well, it's messy. So the Q and B convolutions, I wrote down their definition, right? I wrote down their definition in terms of Q or in terms of Q binomial coefficients and B finite differences. Those are the only definitions there are. There's no root definition. There's no random matrix model. And so I can't do the root trick I did, the one-page proof of the classical one. And so we get to a lot of combinatorics. We define this map on raising B factorials, which maps raising B factorials to Q Pochhammer symbols. And we just extend linearly. So this is a basis of polynomials of degree n. So we extend this map linearly. And our theorem is that this is going to be the substitute for exponentiating our roots. But we can't do anything clever here anymore, because notice this is no longer precomposition. Before it was precomposition, everything was so well behaved. Now we just have some linear map, which is defined on some horrible basis. But we do prove this. This is true uniformly on compact sets. And the way we prove it is based on this Q Lagrange interpolation formula, which is a pretty cool formula. It's just like Lagrange interpolation, except it does everything in terms of Q binomial coefficients. Has a nice little proof. And so using this and some careful, combinatorics, we get this theorem. And I don't really write it, but just in the way that the toy example happened, you can use this theorem to then take the result that the Q multiplicative convolution preserves Q log mesh, and you can get the fact that the b-additive convolution preserves B mesh. So this serves as an interface between these two generalized realms. I should say on this slide, this is very mysterious to Jonathan and I. I would love an explanation for what's happening. I have some rough intuitions about how maybe this corresponds somehow to the Q exponential, one of the Q exponential functions, and taking truncations of it or something. But I really don't know, and I think there should be some better analytic explanation that's happening here, rather than just look at this Q Lagrange interpolation formula and it happens to work. So there's still questions to be had here. OK, I would be remiss if I didn't say something about MSS. So as Jonathan talked about in the last talk, submodularity, we love it. It's a really great thing. Does submodularity exist in the b-additive realm? And that's a conjecture. So you take u alpha instead of 1 minus alpha d. Now you do 1 minus alpha finite difference. There's some technical note here where you have to do the shift the other way to bound things from above. You get immediately a triangle inequality. It's not hard to prove. But then the question is, can you get something stronger? So this would give you, if you have some polynomials you're interested in studying that are defined by finite difference equations, then you'd be able to get really fine control over the roots using this method. And this is another example of where I think there's something that we're missing here for the submodularity proof, because if you try to extend the methods that were currently known for submodularity, they fall apart. And that's just something in general that I think is really interesting about this b-additive and q multiplicative realm from a theory point of view, is that often when you have a result in the real polynomial case, the real rooted polynomial case, you can generalize it to the b-additive case. And the b-additive case is strictly more general. When you limit b to 0, you recover your original result. But the tools at your disposal in the b-additive case are much more limited, which means if you have some result that you think abstracts the b-additive case, you should be able to prove it in that realm using your limited tools. And all those tools limit to tools in the real rooted case. So this to me implies that there should be some way to prove submodularity using only things like interlacing and polar derivatives, which is very far from the current proof. Because that's kind of all we have here at the moment. Or maybe we need some really new machinery in the B-mesh world. But I think it actually is helpful to limit the tools you have when working with real rooted polynomials, because there's so much out there. And it's pretty interesting to test if you think that there's a generalization in the B-mesh world to limit those tools appropriately. So yeah, limiting alpha to 0, just like before in the classical case, gets you the triangle inequality, and limiting b to 0 will limit these finite differences to derivatives, so you'll recover the MSS result for the classical convolutions. OK, and just a few words about future directions. Yeah, I think the most interesting question to me is there a classification of all linear operators which preserve one-mesh polynomials? Just discrete Polier theory in a nutshell. This is a hard question, I think. We've kind of answered the most obvious questions at this point. And if you look at it, it seems like the b-additive and the q multiplicative realms are splitting real polynomial theory in half. Right? We take the results about difference operators. Those become results about shift operators in the b-additive case. You take results about diagonal operators. Those become results about the q multiplicative case. They get log mesh results. So it's really interesting to me to try to unify this theory. I don't have a way to do it at the moment. And I think key to this, of course, just a la Boccia and Brondin, is there an analog of real stability? And so it's really unclear what the analog of mesh is for multivariate. I don't think it's a condition about spacing of the roots per se. It could be, but it's very unclear what it should be if that's the case, because these things kind of become more ambiguous when you have infinitely many roots. And if you came up with an appropriate multivariate polynomial framework, could this explain this connection in a much more intuitive way? And then finally, is there a random matrix model which interprets this? So this Q stuff in particular is really interesting. And Q stuff shows up a lot in quantum Lie algebras, and you often have some noncommutative ring, which in this noncommutative ring, all these Q identities just become true. And I'm pretty interested, but I don't know enough about this to pass judgment on it. So if anyone does, it would be really interesting to see if we could somehow get a random matrix model, or even just symbolically get something of that form which yields these modified convolutions. That's it. Any questions?
Do you expect this random matrix model to have some kind of discrete flavor?
Yeah, definitely. I messed around with it for a while, but I really need to sit down with somebody who has a lot of experience with. I think somehow, underlying it's going to be some of this well-studied quantum algebra stuff. Pretty interested to see what comes out of that. Thanks.